Hey, in this week's lab, we decided to look at the physics of extreme sports with ropes. Specifically, the purpose of this lab was to evaluate an oscillating object on a spring using Newton's second law, which is V final is equal to V initial plus F net divided by mass times delta T, as well as the energy principle, which is work, which is equal to delta E, which is equal to delta K, the change in kinetic energy, plus the change in potential of gravity, plus the change in potential energy of the spring, which should all be equal to 0. And the problem with this was to predict the motion of an object on a spring as it oscillates in the x and y directions. And we found that the model approximated the observed spring's motion well, however not perfectly, which we will talk about later on. In Tracker, I followed a series of steps to properly extrapolate the data from the video that will be used later. I first set the calibration stick to 0.7 meters and secured my axes with positive x in the right direction and positive y in the up direction. I then added points of mass as the ball swung to provide x and y coordinates that I downloaded into a CSV file to use in my code. As far as Python goes, there were a few initial conditions we needed to put into our code, which you can see on the left hand of the screen. On the right, you see the equations that I used in the work that I did to find the spring constant and the initial relaxed length of the spring. To find the spring constant, I use the period equation, which is T is equal to 2 pi times the square root of mass divided by the spring constant. We know that the mass of the ball is 0.402 given to us by the lecture video. So using that in the period that we can find using the Tracker video, you can find that the spring constant is equal to 5.9 newtons per meters. Now having the spring constant, when the object is at rest, the magnitude of the gravitational force is equal to the magnitude of the spring force, which you can see there is the force of gravity is equal to the force of the spring. That just, knowing the definitions of the force of gravity and the force of spring, we can use mg is equal to ks to use this to find the initial, the relaxed length of the spring. And then you can see to the left that these equations that I wrote out to the right are put into my code directly. The next thing I did in Python was actually use Newton's second law in the position and the velocity format, as well as the energy principle, to code the model. We know that the net force is in this scenario is the gravitational force and the spring force. So with that, we can calculate the velocity and the position of the ball. As you can see on the right, I translated the velocity and the position format of Newton's second law into my code in order to solve for the F net and then the velocity and the position of the ball. Then to find the change in energy, the equation you see on the left has been inserted into the code as well. Now that we have discussed important parts of the code, let's run it. As you can see here, the red ball, which is the observed ball, follows closely to the blue ball with some deviation. When you look at this graph, you can see that not only on the visualization that there is a deviation between the red ball and the blue ball. The red ball being the red line, which is slightly behind the blue ball. So it seems that the computer model almost overestimates the motion of the observed model. This is the graph that computes the module's energy. Note that the yellow line, which is the total energy, is equal to 0, satisfying the energy principle because no energy is gained or lost to the surroundings. The red line is the spring potential energy, the blue line is the kinetic energy, the green is the gravitational potential energy, and yellow, like I said, is the total energy of the system. The gravitational and spring energies are opposites of each other, and the kinetic energy oscillates at a much faster rate. The kinetic energy changes as the velocity changes. When the spring is fully stretched, the velocity is equal to 0, and as it travels to compression and stretch, the velocity increases and decreases. This accounts for its different frequency. The gravitational potential energy is based off the y position, so it will increase as the mass moves more in the negative y direction. The spring potential energy changes based off compressed and fully stretched, which are when it's the highest, which is why it's opposite of the gravitational potential energy. If we tried to estimate the period of oscillation of the spring, which is the time in seconds it takes per cycle based on the x and y coordinates of our experiment, this is what we would find. Here we could see that the time it takes for the mass to reach its initial x and y coordinates is different. It takes about 1.6 seconds to return to the x initial, which is negative 0.08, and it takes about 1.04 seconds to return to the y initial, which is negative 0.69. This might mean that the object is moving at a different velocity in each direction.